Hello grade 11s, welcome to my channel, and hopefully I can be of some kind of assistance in your preparations for your exams. I don't know if you've already written your media exams already in physical science. If not, this may find you well in time during your preparation. If you have already written, this may help you to work towards your finals. But if you are a grade 12 who is subscribed into this channel, I would advise you to watch this video because most of the content here is essentially examinable in your matric syllabus. Without wasting time, let's just get into the business of the day. So instructions. Operational ones like here, how you are to number the answers. You have to use the system of this paper, and then for formulae and substitutions and any calculations, it's important to show them. And then of course, if you are asked to motivate for some choice, then you have to keep it brief, but you can use absolutely anything that is applicable. This can be an equation, this can be some inference, it can be a principle, anything, okay? So again, still sticking with the operational instructions, we are rounding off our final numerical answers to a minimum of 2 decimal places. This means 2 or more, all right? And then start each question on a new page, okay? It's of note, to keep in mind that diagrams are not necessarily drawn to scale, so don't try to read too much in the diagrams per se, but do learn the implications behind those diagrams. All right, let's get to question 1. So we've got our question 1 here. Well, they chose to just write it so small. Okay, various options are provided as possible answers to the following questions. Each question has only one correct answer. Of course, you may find a scenario where you've got more than one correct answer. Of course, of the correct answers, you have to choose the most correct, okay, or the best answer. At times, they are equally correct, so you just have to choose one. It's just a trap to get you mad, all right? Choose the answer and write only the letter A to D next to the question number, okay? And we're given a taste of that for 1.5, it could be option E, all right? Let's get to question 1.1. It says now a negative charge of 1 microcoulomb, which is free to move. Okay, our charge is a 1 microcoulomb, and of importance is that it is free to move, okay? Is placed at a distance 2r from a positive charge of 4 microcoulombs. All right, not a problem. And then we can see that we're dealing with Coulomb's law, essentially. What does Coulomb's law tell us? It tells us that the electrostatic force between 2 point charges is equal to the constant multiplied by the product of the 2 charges over the square of the distance between the 2 charges. Now we're told here, okay, this was initially 2r, okay? And now we're given a scenario that says, which one of the following statements regarding the minus 1 microcoulomb charge when it is at distance r? So now distance r is half of 2. So we're essentially halving the distance. Okay? Because to move from 2 to 1 is just halfway, is it not? Okay, now of importance is to use this equation. We know that the electrostatic force is effectively this situation right here, and it is defined by this expression, okay? Not a problem. So what do we do here? Well, what we do is simple, because we know that what is changing is on the denominator, so we just leave the numerator as it is. Just keep it as it is. Sometimes you just have to choose your battles. So we've halved our r, okay? So what happens? When you square that, you're going to get, you're going to get still the numerator as it is, But here now we're going to have 1 over 4r squared. Okay. And then now when you divide by a fraction, it essentially multiplies in front. Now we're going to have k q1 q2 over r squared. Guess what? This is basically 4 times the electrostatic force. So essentially, what is it saying now? It says the electrostatic force experienced by the -1 microcoulomb charge will essentially increase by 4 because we have halved the distance. So this is one of those questions that you cannot just guess the answer. You've got to understand what's going on, okay? Don't worry about the 2r. It's going to mess your head a little bit. Don't allow it to, okay? Which one of the graphs below represents the correct relationship between force F on a charge? So if we're talking about force on a charge, it's an electrostatic force, and the electric field E. Okay, now we know that, okay, we understand that the electrostatic force is actually defined by the charge multiplied by the electric field. F equals QE. Or you can say an electric field at a point is the electrostatic force experienced by that charge in that position. All right, because E is going to be F over Q. Great. Now we know if we keep our charge constant, essentially, what happens? We know that the electrostatic force will essentially be directly proportional to the magnitude of the electric field. All right. So if that is the case, we expect a graph that passes through the origin and it's positively sloped like that. Okay. So this simply says if the electric field increases, it means the amount of the force increases, or vice versa. If the electric field decreases, and so will the force, okay, provided we're keeping our charge constant. So the answer there becomes B. So at some point, always attempt to work out the formula that may be governing any graph that you are given, because that way you will not be able to faff around, and at the same time you don't have to cram most of these things. You just will be able to extrapolate that information, or should we say interpolate. Yeah. 1.3 says the leaves of an electroscope, okay, in the diagram below are positively charged, and we can see that here and there. Okay, great. So now it says an object is brought close to the plate, the leaves diverge more. So if they diverge more, what does that tell us? It tells us that this particular object is definitely positively charged. Okay, great. And of course, we know the electrostatic force is directly proportional to the charge. In a way, the force that will be experienced is going to be a bit greater if the charge or the magnitude of the charge increases. As a result, what happens? There will be a more diverging leaf than it was initially. Okay, so we can say now it can therefore be concluded that the object is most likely positively charged. Could it be negatively charged? I don't think so. Is it not charged at all? If it wasn't charged at all, then there would be no further movement of our leaves of our electroscope. So it releases positive charges. I wouldn't be too sure about the releasing of positive charges. Why? Because usually these are fixed in the nucleus. Unless we're dealing with some radioactive substances, the lanthanides and what, those ones are radioactive, and essentially their nuclei are unstable. So the positive charges can spread around, but I wouldn't be too sure about, a normal scenario. So I'm not too sure about D, but I would go with A. And of course, you have the luxury of the memorandum of this paper, so do have a look to confirm that answer. Now it says two charged objects repel each other. Again, we're still dealing with electrostatic forces here, or Coulomb's law. So if they repel each other, it means they carry the same type of charge, be it positive or negative. Now they repel each other with a force F when they are separated by a distance d. Okay, so we're still dealing with Coulomb's law here. The distance between the charges is reduced to 1/3 of d. Okay, so if we're doing that, what are we doing to the force? Remember, if we decrease the distance, the force increases, right? Right. So we can simply say, fine, we're still dealing with Coulomb's law here, where we're talking about the electrostatic force equaling a constant K multiplied by Q1 multiplied by Q2 over R squared. But now we can see that we're manipulating the denominator here. We're putting 1/3 of d, and then we're squaring that. Perhaps we want to use d here, so that we can be able to see what we're doing. And then of course we have our numerator there, and then we still have that situation ongoing. But now when we square here, we get 1/9 d squared. And then of course when you're dividing by a fraction, that 9 multiplies in front, and we're going to have our K Q1 Q2 over d squared. And what is that? That is 9 multiplied by that electrostatic force. So it increases by 9-fold. So it says the new force in terms of F will now be definitely d. Again, it's one of those questions you must not try to guess, but you work out. Okay. 1.5 says, which one of the following has the strongest forces between its molecules? So if we're talking about forces between molecules, we're talking about the so-called intermolecular forces. Okay? And they are sometimes called van der Waals forces. Okay? VDW. So these are the van der Waals forces. A Dutchman, right? Right. Then we've got fluorine gas, chlorine gas, and bromine, water, and iodine, water. Why am I saying water? These are of high molecular weights, so they will be liquid at room temperature. Whereas these ones are of light molecular weights, so they will be gases at room temperature. Please know these things. They are very important. Now, we can see here that these are all non-polar molecules. So what are the forces? The forces are the so-called London forces. Okay, these are the weakest of the van der Waals forces. Okay, greatly. So basically they all have London forces. But we also know that London forces increase in strength with an increase in the molecular weight, or should we say molecular mass. Sometimes this may also be looked at as the number of electrons increase. Okay, so that means the more electrons involved, the greater will be the strength of that London force, or at least the molecular mass. Now, which one has a higher molecular mass of these ones? It's certainly iodine, right? Yes, because that has on the periodic table, you will see that it's lower than the others, and therefore it is heavier. So can you see fluorine, chlorine, bromine, and then we've got iodine there. It has a molecular weight or molecular mass of 127. So if you double that, we are going to certainly have a higher molecular mass. Or you can alternatively look at the number of electrons. That number of electrons, this one essentially has 53 electrons against 35 of bromine, against 17 of chlorine, against 9 of fluorine. So basically there's more electrons involved or there's a more molecular mass involved. So essentially the London forces of iodine water should be a bit greater than the others, even though it is of the same order, but the strength is going to be different. So the answer here is essentially D. Okay, now just to expand your knowledge, how does a nonpolar molecule end up with attractive forces between the molecules? Well, if we take for example and say there's our molecule, let's just see that this is our molecule. Okay, so we've got the nucleus here, which is positively charged, right? Right, and then we've got an electron orbiting in its orbit. There's one electron, and then there's another electron, so in its orbit like that. So what happens? Because we know that these electrons are in constant motion, sometimes we refer to that as spins. Okay, so let's say this one is spinning in that direction and that one is spinning in that direction. What happens? Because the electrons closest to the nucleus are tightly bound, they have lesser velocities than the what we would call valence electrons in the outer energy structure. Those ones are much freer to move, so they move at higher velocities. So now a scenario will come down such that we've got this atom now, the very same atom that we've got with this positive nucleus. Then we see that, well, there is our electron that was orbiting. It's just moved that smaller distance. Whereas this one, because it's free to move, it is now in that position. So what happens? This creates a partially polar, side. So we use the small letter delta minus. So that one becomes partially negative, whereas this other half becomes partially positive. So this is the so-called instantaneous dipole in a nonpolar molecule. Okay, and then if we do the same, say fine, there is another molecule of the same order as this one. Okay, doesn't necessarily have to be of the same order though. So we've got our nucleus, which is positive, and then we end up with these electrons that were orbiting looking like that. Okay, so what are they creating? They are creating yet another polar end. These are instantaneous situations. That's why we call them induced dipole induced forces, or the London forces. And then of course we know that this becomes negative against this one, which is positive. And what happens? The positive end will attract the negative end, and that's what we call a London force of attraction. Okay, so that's how it happens in these nonpolar molecules. I was just expanding your knowledge. Let's move before we lose time. Okay, question 6 says, oh, by the way, if you think about it now, if there's more electrons involved, then that would mean there would be more of the same order. And that means, for example, take an object like that and then another one like that. Then you've got this little force of attraction between them. When it's one, it's easy to snap it, right? But if you've got the same two objects that we had, but now you have these forces, maybe you've got 3 of them. Take a rope, for example, and attach it like that. This one is going to be a lot harder to break than that one, is it not? So that's why we are saying the more electrons involved, the stronger will be the forces of attraction. Okay, so there's a lot we can say here, but I do hope and believe you will have learned most of what you need. Okay, so let's go on. 1.6 says sodium chloride. All right, we know that this is an ionic substance. Okay, a solid which is soluble in water Why? Because water is a polar molecule. Okay, now it says, which one of the following describes the intermolecular forces that exist between the sodium chloride and the water in solution? Now, what do we know? We know that fine sodium will break into chloride ions and sodium ions in solution, right? But now we've got a water molecule that we know has its own behavior. We've got an oxygen molecule there attached to hydrogen molecules. Okay? So those are the hydrogen molecules and then the oxygen molecule. And what happens? Because oxygen is highly electronegative, it will pull those electrons towards itself, making this end a negative end, whereas this end remains partially positive. Okay, so what happens? The chlorine or the chloride ion will be attracted to the positive end, whereas the sodium will be attracted to the negative end. And these ones are the so-called ion, because now this is an ion involved. So this is an ion dipole, because water molecule is a dipole. So we call them ion dipole forces. All right, so it says that is going to be A. Okay, a bit of theoretical knowledge is important in this case. Now 1.7 says 2 moles of hydrogen gas at STP. Now, once we talk of standard temperature and pressure, we know that 1 mole of any gas occupies a volume of 22.4 decimeter cubed. Okay, that you need to know. At STP, be it a real gas or a noble gas or what we call an ideal gas, it will occupy that volume, 1 mole of that gas. Okay, it doesn't matter which one. This is the basis of this formula that says the number of moles is volume over the molar volume at STP. So that's how we derived that volume, by knowing this piece of information. Okay, so now we are told here 2 moles of hydrogen gas at STP. So now we definitely know that if we want the volume, we know that V, being the subject of the formula, is going to be number of moles multiplied by the molar gas volume. So this one becomes 2 into 22.4, which becomes 44.8 decimeter cubed. So essentially the answer becomes D. All right, so please know these things. They are very important. Again, it's one of those questions where you are going to couple a bit of theoretical knowledge and some kind of a calculation thereof. Okay, now 1.8 says how many moles of potassium bromate, okay, please make a habit of knowing these names. This is potassium bromate, are required to prepare 0.0700 moles of bromine water or bromine according to the reaction. So we can see a potassium bromate reacts with 5 moles of potassium bromide plus 6 moles of nitric acid. This produces 6 moles of potassium nitrate plus 3 moles of bromine, which is what we're interested in, plus 3 moles of water. Great, so now we want to compare these two. Now we know here that the number of moles that we got is 0.0700 moles. Now what do we know? The molar ratio is that 1 mole of potassium bromate produces 3 moles of bromine. So now what do we do here? We can say this tells us that the number of moles of our potassium bromate is going to be 1/3 of the number of moles. Maybe let's write it nicely. Number of moles of the bromine. Okay, now let's just do the things. Just write 0.0700. What does that give us? So we have to put that in the calculator. So we've got a third of 0.0700. So what do we get? We get a 0.023 to 3 decimal places. And then what is that? That is A. Okay, so I don't know why it's doing a heart. Okay, now that is the story that you have to tell there. Again, it's one of those where you need to know the molar ratios. Basically, this is stoichiometry. Now let's see, 1.9 says the limiting reagent. Now when we talk of a limiting reagent, we know this is the one that gets expunged completely in a reaction. In a chemical reaction is one that has the largest molar mass? Not necessarily. It doesn't have anything to do with the molar mass. Has the smallest molar mass? Again, it has nothing to do with the size of the substance itself. But is it the one in excess? No. The one that gets used completely is the limiting reagent, because when it gets finished, then the reaction stops, even though the other substance was still available for more action if it was to receive it. All right. Now, what is the mass percent of each element in dichloromethane? So we are being given here the molecular formula. Now, for example, you can just choose carbon. Okay, sometimes questions like this, you just need to be smart about your approach. So let's just look at the percentage of carbon. So we know essentially that the mass percentage is going to be the mass of carbon over the molar mass of this compound here, which is CH2, Cl2, right? Multiplied by 100%. So let's just find out what do we get. The mass of carbon is 12 over the mass of this thing. Okay, it's a bit complicated. So this is going to be 12 plus 2 for the hydrogens plus 35,5 times 2 for the chlorine. Then we multiply that by 100%. So let's see, what is that? So we've got 12 divided by 12 plus 2 plus 35,5 times 2. And that stuff we multiply by 100. So I'm getting a 14,11 to 2 decimal places. Maybe 1, 2, whatsoever. It doesn't really matter. Maybe let's leave it here. Then now when we investigate here, we've got the percentage of carbon as that in B, and if that doesn't have any other issues with the other options, most likely that is the one. But do double check the hydrogens and the chlorine. But remember, you use the numbers that you see there. So for hydrogen, you're going to use 2 because there's 2 molecules of hydrogen. If you're using chlorine, you're going to use 2 molecules of chlorine. So that would be 35,5 times 2 over the smaller mass, and then you multiply by 100. You should be getting those values. All right, so that's it for now. Let's just move on to the next question. Okay, so we're going to be drilling question 2. Now, I told you, or maybe not you guys, but if you are someone who's watching these videos not for the first time, be it grade 12 or grade 11 or even grade 10, doesn't matter. You know that I always tell you that the MCQ section will always give you a sneak peek of the topics you're going to be examined on more extensively in the longer questions. So do skim and scan the MCQs if you are not willing to start with them, to prepare your mind for the action that's coming next. Okay, so let's get to question 2 and start doing our things. So now we're dealing with electrostatics. This is a topic even grade 12 needs to know. So please, it is examined almost at the same level as it is examined in grade 11. So you cannot run away from this one. Now I told you 3-point charges, Q1, okay, sorry, and then Q2, and then Q3, okay, carrying charges of plus 6 microcoulombs, minus 3 microcoulombs, and plus 5 microcoulombs respectively, are arranged in space as shown in the diagram below. The distance between Q3 and Q1 is 30 centimeters, and that between Q3 and Q2 is 10 centimeters. And we can see all of that piece of information is given right there. So there's no manga business here. And then of course we've got our Q1 here. Where's Q1? There you are. And we have gotten our Q2 right there, and we have our Q3 right there. So always make it a point that you've clearly identified what you are given so that you don't struggle. Now it says state Coulomb's law in words. So that is nice because this is now a principle that we already used, didn't we? We've already used in the MCQs. So now we are to give more. So do you see what I mean by the things that I say? So now Coulomb's law says the electrostatic force between two-point charges is directly proportional to the product of the charges. Okay? And inversely proportional to the square to the square of the distance between them. Okay? Please make a habit of doing these things. Trust me, these things take time to write down. So when you practice, just do things properly because you will learn to speed up while you don't leave out anything. So please, no bad habits. So this is easy, 2 marks. So if you capture those two proportionalities, that's usually what is important. Okay, let's go. 2.2 says draw a force diagram showing the electrostatic forces exerted on Q3. So this is our reference charge, Q3 by Q1 and Q2 respectively. So let's look at Q3. Q3 is a positive charge. It's a positive point charge. So the relationship between Q3 and Q2 is going to be that of attraction. So meaning Q3 will be pulled towards Q2. Okay? So if we place our Q3 here, Q3 will be pulled, will be pulled vertically down. Is it vertical? It looks slanted. Sometimes my orientation is not, oops. So anyway, so that is the force that we're going to get. What is this force? This is the electrostatic force by Q2 on Q3. Okay, that's how we can label that. And then of course, what else? Now we can see that Q1 is positively charged as well as Q3 is positively charged. So these ones are going to repel each other. So Q3 will essentially get a force in that direction because it's being repelled by Q1. So this is going to go in that direction. Okay, so this is now the electrostatic force of Q1 on Q3. Okay, please make a habit of labeling things properly. Okay, not a problem. So we know here that between them we're going to have 90 degrees. Okay, so that is the most important part. But at this point we're interested in the two forces. As you could see, there were just 2 marks on offer there. Okay, great. So that is important. And then of course they said a force diagram, so you can label this one as Q3, that point right there. I don't know if it is necessary, but I don't think it is. Let's just leave it alone. Now it says calculate the net force exerted on Q3 by Q1 and Q2 respectively. Okay, so they're saying here there's a lot of work you need to do, and definitely there is. Now we need the magnitude of this force, and we also need the magnitude of that force, right? Because through our parallelogram method, you know when those two forces are going in that direction, so we're going to need stuff like that, right? Because we just need to draw a parallelogram. Okay, and if we draw that parallelogram, although this one is not the best parallelogram you can ever ask for, yeah, doch, maybe I should do it better. Yeah, yona lonto bafowethu ifuna ukungihlanyisa kahle kahle. Alright, so that is the story. So we know that this is the resultant force. Okay, it will go in that direction. So there's 2 things to consider. We need to think about that theta, because a resultant force, when they say calculate the resultant force and they don't say just magnitude, you need to think of direction as well. It's going to be super important. Of course, this was another question, so I was just showing you what you need. So basically, no manga business here. So we can start 2.3 here in this man. We know that, of course, we've got this force going up like that, and we've got that one going like that. Although it doesn't look like the way it's supposed to look, guys. So we know that our resultant force is going to be directed. Actually, let's just do it better. I think the head to tail method is going to be a lot better. Okay, so now if we shift that force to put it here, because we want the head to tail method, and then our resultant force is going to go in that direction. Great. So there is our resultant force, there is our other force, and there is our other force. So this is still the resultant force. This is the force by Q2 on Q3. This is still the electrostatic force by Q1 on Q3. And then that would be the electrostatic force resultant. All right, but now we know we need to consider that angle theta there, because without the angle we have not done any justice. But we know that, well, the angle between these two forces was 90 degrees, so it remains 90 degrees like that. Easy. Now we can just work things out. We can say, fine, we first have to calculate one of these forces, and then we keep going. So let's start. The Fe by Q1 on Q3 is going to be Coulomb's constant Q1 Q3 over r squared, okay? And then this is 9 times 10 to the 9 into, now what was the magnitude of Q1? It's plus 6. Now that is microcoulombs, that is times 10 to the minus 6, into Q3 is plus 5 times 10 to the minus 6, okay? Now this is over, the distance between the two was 30 centimeters, so basically this is going to be 30 over 8,000. You change this to a meter, and then you square the thing. Okay, try to always do a bit of work to simplify your life. So this is 9 times 10 to the exponent 9 into 6 times 10 to the minus 6 into 5 times 10 to the minus 6. All of that over 30 over 1,000. That is squared. Okay, so I'm getting 300. I'm getting 300 newtons. Now remember, if it is positive, that is this is repulsion. That's the direction, because this is a force, okay? And then we can go on and say, well, we want Fe of Q2 on Q3. It's going to be, at this point, you don't really need to be doing that. You can just go straight to the substitution. We have shown it above, so we don't need to show it again. So this one now becomes minus 3 times 10 to the minus 6 into, this one is 5 times 10 to the minus 6. All of that stuff divided by, what is the distance between the two? It was 10 centimeters. So 10 centimeters. Oh yeah, I made a mistake. To convert centimeters to what you call to meters, you divide by 100. Sorry guys. Okay, so this is obviously going to be 30, right? Let's just check. Okay, now that is messed up. So we've got 9 times 10 to the 9 into 6 times 10 to the minus 6 into 5 times 10 to the minus 6 over 30 divided by 100 squared. It's 3, okay. So this is just 3 newtons. Okay, not a problem. So there was a bit of a situation here. So this is over 100, and then we square that. Okay, so I'm just trying to save myself from a bit of a disaster. So that is a minus 3. So now we come here. Just change that to a 10. Alright, so what do we get here? I'm getting a minus 13,5 newtons, which is basically just 13,5 newtons. This is now attraction. When it is negative, it means attraction. Okay, so now that we've got these forces nice and easy, to do the resultant, we just use Pythagoras, because that's essentially what is important. So we can just say, then we know that the Fe R is, okay, maybe let's square it, is equal to the Fe of Q2 on Q3 squared plus Fe Q1 on Q3 squared. That is because of Pythagoras. Okay, make it a point that you do this thing properly. This implies that Fe resultant is going to be equal to the square root of, now we're putting these ones, is going to be 13,5. Of course, you can put it negative, it's fine. It won't cause any harm. Squared plus, that one was 3 squared. Okay, so the resultant, remember, we will always consider it positive. Okay, because that's the hypotenuse side, so we'll never take it for a negative. Ever. So we do it square root of 13,5 squared plus 3 squared gives us this number of 13,8, 3 to 2 decimal places. This is going to be newtons. But now we've got to consider the direction. If we're looking at this one, this is the south, okay? So this is south. And that is going to be west. So basically we're moving west of south theta degrees. Okay, so we've got to think about how we're going to work that out. We're going to say this is going to be basically from the south. We're going to go arctan, because remember we've got the opposite and the adjacent, so that's a tangent. Arctan of, what is that? The opposite is that one, which is the Q1 on Q3, which is basically 3 over, now we're going to focus on that 13,5. So we're just not going to worry about the negative at the moment. Okay, now we're going west. So this is going to be 13,83 newtons. Which direction? South. From the south, we're going to go how many degrees? So we're going to say shift 10 of this 3 over 13,5. So this is 12 degrees. So we're going to go from the south, we're going to go 12,53 degrees to the west. Okay, so there's plenty of ways you can express the direction, but if you don't include the direction here, you're going to be dead. Of course, I'm integrating things so that we do not have a problem. So let's go for it, guys. There's a lot of work on our shoulders here. Anyway, so I will. Itheni ngoyandilinga lento. Sundilinga wena man. Uyandiphela tyhini. Now, we've done the resultant essentially. So we know that for formula, you get a mark. For substitution, you get a mark. But this little thingy, converting that to meters, is an important step. So this one is 4 marks, right? Right. Here is just the substitution and that conversion. That gives us 2 marks. And that thing is that one. So we've got how many? 1, 2, 3, 4, 5, 6, 7. Okay. And essentially 8. So maybe I gave too many marks, eh? Yeah, doch. Sometimes it happens, you know. Anyway, we've got the 8 marks in the bag, no matter what. All right, let's get to 2.4. Now, 2.4 says 2 identical spheres. What do we mean identical? They are of the same weight or size, volume in space, but probably not same charges, okay? A and B are carrying charges, you see, plus 5 nanocoulombs and minus 10 nanocoulombs, respectively, are separated by a distance of 30 millimeters. P is a point located at 15 millimeters from sphere B, as shown. So this is nice because we can see what we're dealing with. What is of note? What is the charge of A? It is the plus 5 nanocoulombs. that one of B is minus 10 nanocoulombs, okay? Now, the spheres A and B are allowed to touch, okay? Because they obviously are attracting each other. They will attach and then return to their original positions, meaning they will still be 30 millimeters apart after they have come together. So this is the most important part to make sure is ingrained, and you can see this is information that is given prior to any question. So this is the scenario that we have before we are asked any question. So let's go for them. It says now define the electric field strength. So do you see we worked out something on the MCQs? Now it's coming again. So we've got here 2.4.1. So we know that this is, what can we say? It is the electrostatic force. It is the electrostatic force experienced by a unit positive charge at that particular point. Okay, so the electric field strength at a point is the electrostatic force experienced by a unit positive charge at that particular point. If you have forgotten, think of this one. Fe is equal to QE. So when you work out the electric field, you simply divide by Q. So it's going to be force per charge. Okay, that is the most important. So sometimes you don't want to complicate your life. You keep it simple. You move on. The question is why positive charge? Because this is what was experimentally done. So it's a historical thing, but it can be essentially any charge whatsoever. Okay, it says now 2.4.2, draw an electric field pattern between spheres A and B after touching. Okay, so this is 2.4.2. So we know that, well, say this is our A here, and then that is our B right there. We know that after they touched, let's check what will happen. They will be negatively charged because we just simply add. So it's 5 times 10 to the minus 9 plus into minus 10 times 10 to the minus 9. And then we divide that by 2. So I'm getting a minus 2.5 nanocoulombs. So they will be both negatively charged. Maybe we can indicate that somewhere. So we know that the electric field lines will essentially try not to touch. Because they will be repelling each other, right? They will be repelling each other. So they'll be doing stuff like that. So maybe let's remove this one. It didn't come out nicely. I've got a nice tablet here that does things, you know. It does things much more smoother. Okay, now we can just simply do our stuff whichever way we like. We really don't have to sweat. Okay, so I'm just going to keep it simple. So now remember, to a negative charge, the field lines are going in. Okay, they are going in. Superb. So that is the story that you want to show. Of course, it doesn't have to be accurate, but you're just trying, you know. You are just trying buff words. What does it hurt to try? you know, it doesn't have to hurt. We are just simply trying. Okay, there we are. We've done it nice and easy. So now 2.4.3 says, which sphere has an excess of protons before they are contact? Obviously, the positively charged one will have an excess of positive charges because it has a deficit of electrons, which are negative charges. So this is basically A. So now 2.4.4, it says calculate the new charge. So the new charge is going to be equal to QA plus QB all over 2, right? So let's do it. This is 5 nano, it says to the minus 9, plus into minus 10 times 10 to the minus 9. All of that stuff, we are halving it. Now I got minus 2,5 times 10 to the minus 9 coulombs. So please verify that one in case. You know I'm taking it too easy, but I've already calculated, so I don't want to waste any more time. So essentially here we are getting 3 marks. So it's formula, substitution, the answer. And here we're just scoring 1 mark. And then now the pattern, I guess the direction of the field lines is important, and the fact that they don't touch or overlap is important, and identifying that they are actually negatively charged. So probably that's how the 3 marks are arrived at. Okay, so we've got 2.4.5. It says now calculate the magnitude of the net electric field at point P due to A and B. Now remember, this question here does not say anything about at what time interval are we doing this. But the opening statement said these ones were allowed to touch and then they returned to their original positions. So we'll take the assumption that this question is based on the fact that they are now negatively charged. Okay, great. So we know that find the E net or the resultant. I don't like this word net, but yeah, whatever. The E net at P is going to be basically the electric field due to charge A plus the electric field due to charge B. Is it not? Yes. So what do we understand? We know that we can use Coulomb's law to do this, because that's what we've got. It is what will make our lives a lot simpler. Then now we know that this is 9 times 10 to the 9 into the charge A is now minus 2,5 times 10 to the minus 9. Okay, that's the new charge. Divide by. Now the distance to that is going to be 30 millimeters plus 15. So that's 45, right? 45 divided by 1,000. So these are millimeters, we need to convert to whatever that is, okay? And then we're doing the same here. 9 times 10 to the 9 into minus 2,5 times 10 to the minus 9. Nay, because they have equal charges now, but they're exerting this at different distances. This one is basically just going to be the 15 over 1,000, and then we square that thing. So let's see what we get. So we've got 9 times 10 to the 9 minus 2,5 times 10 to the minus 9 over, we've got 45 divided by 1,000. That's squared. We are adding 9 times 10 to the 9 into minus 2,5 times 10 to the minus 9. Divide by, this one is just 15, divide by 1000 squared. So yeah, these calculators are powerful. You can do a big thing quick. So I'm getting a minus 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, comma 1, 1 to 2 decimal places. That is newtons per coulomb. Okay, and you can see here that this is negative, so it's going to the left. So this is just 1, 2, 3, 4, 5, 6, comma 1, 1 newtons per coulomb to the left. Remember, an electric field is essentially a vector, but what is important, we were only asked for the magnitude. So even if you did not think of the direction, nobody will punish you. So we were scoring 6 marks here. So I would say substitutions, those little conversions are important, and then the final answer there, that's the 5th mark, and essentially the formulae, we're getting 1 mark there. So that's how we score those 6 marks. Pretty easy stuff. All right, so let's move to 2.4.6. Yeah, they were asking these guys. So it says now, if an electron is placed at point P, so what are we placing there? We're placing an electron at point P. Calculate the magnitude of force, again magnitude, experienced by an electron. So we know that, well, Fe is equal to QE. So look, we worked this thing out already. So can you see these questions? I'm telling you, what is the charge on an electron is minus 1,6 times 10 to the minus 19. So into this electric field strength at P, we calculated it, didn't we? Yes, we did. And that's going to get done. Khona nje uqhelana kabi okufuna ukwenzeka eningazohlangana nabo kahle. So this is this one. How many numbers? 1, 2, 3, 4, 5, 6. So this is hundreds of thousands. So this is 111,111. So that is that thing. Oh, cos enough. What the hell? Kwenzeke ntoni ke manje? Yes, do the slow. Zifuna ungihlanyisa. Phela ndi illiterate bafowethu. 1, 2, 3, 4, 5, 6. I'm the illiterate person. So, let's see. Now this one was negative, so we can put it in as negative. You know most. So now let's see. This is minus 1,6 times 10 to the minus 19 into minus 1, 2, 3, 4, 5, 6, 1. All right, so I'm getting a 1,78 to 2 decimal places times 10 to the minus 14. Newtons. Okay, great. So at this point, this is fine. We really don't care in which direction, but I mean, of course, it's to the left, but we're told just do the magnitude. So let's just avoid this one because it's a bit silly, is it not? Formula, substitution, answer. That is how you get the 3 marks. Easy, 30 marks there. So let's move on. I cannot waste this page, so let's just use it for the next question. So we've got question 3. Of course, for you should be on a new page, but for me, I can cut the corners. I get it. Visual on twain. Let's see the reaction. Okay, we are here, guys. Question 3. The reaction below is used in the Haber process to manufacture ammonia. So we've got 2 moles of hydrogen gas plus 2 moles of oxygen gas, yielding us 2 moles of water vapor because it's gaseous, right? Now the boiling points of the substances in the reaction are as follows. Okay, we can see hydrogen is minus 252.9, and it already tells you this thing is gas at room temperature. And then oxygen is minus 1,83. Again, it's negative, so it's already a gas in room temperature, which is true, right? Water is at 100 degrees Celsius, and at room temperature, which is 25 degrees Celsius, this thing is liquid. Okay, and you can see the melting points. Now it says define the term vapor pressure. Again, definitions. 3.1. Now we know that vapor pressure, now it is at their pressure exerted by a vapor in equilibrium. With its liquid in a closed system, okay, at a particular temperature. Okay, because remember, the vapor pressure varies according to the temperature at which this is happening. At the same time, it has to be a closed system, because if something escapes, then we can't measure. Right, and this thing, therefore, should be in a way of some kind of an equilibrium. So please make sure these definitions are as complete as possible and they're as scientific as possible. Don't enjoy too many shortcuts that actually leave out pretty important statements. Okay, now it says 3.2. It says now write down the name of the substance in the table that will have the lowest vapor pressure. Obviously, the one that will have the lowest vapor pressure is the one that has the highest boiling point, which is going to be our H2O. So what did they say? Write down the name. So if they say name, so that is water. So 3.3 says name the type of intermolecular force present in H2O. So we know that this is the hydrogen bond. Hydrogen bonding. In H2, this is London forces. Okay? Or maybe say, yeah, let's just say London forces or force, whatever. So we score our marks here. Nice and easy buff words. Easy stuff. Question 3.4 says, which substance is a liquid at room temperature? It is water. So here you can either write a formula because they didn't specify, or the name. 3.5, nice and easy. It says now which substance will have the strongest intermolecular forces? Explain in terms of strength of intermolecular forces and boiling point. So which substance is going to be that? It's going to be water. Okay, because this one has strong hydrogen bonds. Between its molecules. All right, therefore more energy is required to separate the molecules. Therefore, we'll have a high Boiling point. I'm sorry for the writing, it just keeps on fading. So obviously always try to answer as completely as possible. But in any case, it will be water. We've identified why. And then they said we must mention the bond type and the strength, of course, that is the one. And the boiling point, of course, we've said it and we explained why that boiling point is high. It's because of more energy needed to separate those molecules. So 3.6. Now 3.6, which they wrote wrongly, 3.8. How does the strength of intermolecular force, how does the strength of the intermolecular of compound H2 compare to the vapor pressure of compound O2? Right, only higher than Doc, this question, I have a bit of a situation here. What are they trying to say now? How can you compare a vapor pressure and intermolecular force of another compound? That's rubbish, is it not? Because essentially you are comparing apples and bananas. Yes, they are all fruits, but they have different tastes and smells. Come on, let's just leave this question. It's ridiculous. I don't think they phrased it correctly, because in my opinion, they should be asking about the vapor pressure of those two between oxygen and hydrogen. Then I would make an understanding in terms of the molecular size and the intermolecular forces, because they both have comparable intermolecular force strength, which is the London forces. They have differing molecular weights. Oxygen is heavier than hydrogen gas, and as a result we will be able to tell that the strength of those London forces are different. As a result, the vapor pressure of oxygen will be greater than the vapor pressure of hydrogen. The vapor pressure of hydrogen will essentially be greater than the vapor pressure of oxygen for the same temperature, right? So I think here they made an error. You can't compare vapor pressure and an intermolecular force strength of another compound. It's absolutely ridiculous. So we're not going to answer this question. There was an error here, and I'm not even going to waste any time trying to answer such a question. Okay, let's get to question 4. Nice and easy. Nice and easy. So we're going fine, guys. Of course, this is a 2-hour paper, but we'll see if we will be able to make up the time that we need. Yo, there's so many questions. Yeah, let's try. Okay, question 4. Is like this. Methyl benzoate is a compound used in the manufacture of perfumes, okay? Yeah, boy, we know it. It is found that a 5.325 grams of sample of methyl benzoate contains 3.758 grams of carbon, 0.316 grams of hydrogen, and 1.251 grams of oxygen. Let's just double check if these things are all adding up to that stuff right there. So let's start here. 1.251 plus 0.316 plus 3.758. What does it give us? It gives us the 5.325. So yeah, everything is there. So there's no manga business. Please double check these things, because it may be that there's something that is also there, like stuff that is not significant. So be careful. Now I told you, describe the term mole. Oh, easy stuff. 4.1. What is a mole? This is the most basic unit of a substance. In high school chemistry, Of course, what is the most basic? Basically, is the SI unit. You can think of that standard international unit. Thank you very much. So this one was a very lousy question, was it not? And they're giving you 2 marks. That is crazy. Oh, this is the most basic unit of an amount of a substance. Let's be complete. The most basic unit of an amount of a substance. Right. You see, when a question is too easy, sometimes you overlook it and you make mistakes. Then you can lose marks for just a stupid question like that. So it says now determine the empirical formula. Okay, this is grade 10 stuff. You already know from grade 10 how to do this. Of methyl benzoate. Easy. So basically here we need the number of moles of carbon. So it's going to be the mass of carbon, which is 3,758, divided by the molar mass of elementary carbon, which is 12. What is the story there? This is 3,758 divided by 12. The stories that we are getting here are strange. So this is 0,31. Let's just do 3 decimal places, 3 moles. Okay, now the number of moles of what? Hydrogen. It's going to be the mass of hydrogen, which is 0,316, divided by the elementary mass or molar mass, which is just 1. So that stuff is just 0,316 mole. And then we want the number of moles of oxygen. It's going to be the mass of oxygen, which is 1,251, divided by the elementary molar mass of oxygen, which is 16. And what is the story? The story is this one. Is 0,078 mole. So which one is the smallest? Is the oxygen one. So we can say now these ones divide into the ratio of the molar ratios is such that we are going to say for carbon is going to be this number of moles of carbon, which is 0,313. Going to divide by the smallest, which is that of oxygen, 0,078, and that of hydrogen is going to be 0,316 divided by 0,078, and then that of oxygen is 0,078 divided by 0,078. That is effectively 1. And what is that 1? 0,316 divided by 0,078. Of course, we round off to the nearest here. This is 4. And then we go to the other one, 0,313 divided by 0,078. That is also 4. So of course the molar ratio now is 4 is to 4 is to 1. So we can say therefore the empirical formula is C4H4. Oh, okay, that is the most basic molar ratio unit for that particular molecule. How many marks were we scoring for this business? Shenanigan. 5 marks. 5 marks. How is that possible? Well, we know we want the number of moles. So we get a mark for all those number of moles, right? Right. And we get a mark for this double thing is there. Then what? We can get another mark for this thing. So the challenge now is what the hell? What the hell? Perhaps to make up the 5 marks, we can actually mark each one of these guys. So say 1, maybe let's do this properly. Getting this mole, that mole, and that mole is the 3 marks. And the rest is history, right? Right. It doesn't matter how these ones are actually, marked. What matters is what we are doing with it. Now I told you, if the molar mass of methyl benzoate is 136 grams per mole. Now what is the molecular formula? So we know that, okay, now we need the ratio of the actual mass over estimated mass. Is going to be that 136 because that's the actual. The estimated is going to be this one. So it's 12 by 4 plus 4 for the hydrogens plus 16 for the oxygen. Okay, let's see what is that ratio. So 136 divided by 12 by 4 is 48, right? 48 plus 4 plus 16. We get a 2. Oops, that's nice. So we can say therefore the molecular formula is going to be 2 into this empirical formula. Which is going to be C8H8O2. And this is most likely going to be what? Is probably an ester. You saw the word benzoate. Methyl benzoate. That's an ester already. Because we've got the benzoate ion as well as the methyl from the alcohol, which is methanol. So we reacted methanol and benzenoic acid. Damn! That is cool. So this is a damn ester and it smells nice, bro. You can impress a lot of people with that one. Anyway, that was just 2 marks because what mattered was getting this guy and that guy. The rest is seriously historical. So let's do 4.2 quickly. 4.2 says a sample of sodium carbonate was reacted with dilute hydrochloric acid. So what do you know? When you react a metal carbonate and an acid, what do we produce? We produce ikiwa letswai dad. We're going to produce ikiwa. Siproduce lento kuthiwa carbon dioxide. Hayi andiyazi ngesixhosa. Ake itsebele kaSotho. Retla reng he. Hayi ke moya o jwang. Yeah, wona wono he. And then le hydrogen gas. Wa itseba hydrogen gas. Ayiqonda mos. Siqhushumbise lento le. Bulala abantu. Hayi wena soxoka ngamanzi la kimetsi man. Hey. Ke batlile ke le fa poison e jwale. So this is a weak base reacting with a strong acid. Is going to form what? This neutral salt, sodium chloride, okay? But the problem is that what makes this thing acidic is that carbon dioxide will react with water to form carbonic acid, which is the weak acid. So when this carbon dioxide reacts with this water, it will form carbonic acid. So the pH will essentially be less than 7. So this is why when we know for a fact that if you react a weak acid and a strong acid and a weak base, the resulting pH is going to be essentially acidic because of the carbonic acid that forms right here between water reacting with carbon dioxide forming H2CO3, which is carbonic acid. Because this one may throw you off and create an impression that this thing is going to be neutral. No, it's not. Okay, the carbon dioxide is the culprit. As you know that too much carbon dioxide into the atmosphere will end up giving us acid rain. And that thing is dangerous for the plants. So that's why we need to plant them so that they can swallow it up before it causes us problems. You understand. You verstand. Wa itse mos wa ukwishisha wa nkwishisha byanong. Haeba wa nkwishishi ho tla lampama. Ke o jwetsa. Hobane nna ha ke dlale. Ha ke qeke batho monna. Ke ya ba tlhotlhora, ke ba tlhotlhora ka dimpama. Ba tla kgona ho bona hantle. Ke re ha le batle ke le tlhotlhora ke re so le tlo mamela he. Now, we've identified what's going on. So this is an acid-base reaction basically. Okay, now it says now the carbon dioxide gas produced was collected at STP. Heaven. Now we are told this is at standard temperature and pressure. Okay. And occupied a volume of 0.336 decimeter cubed. You know for a fact that this is going to come into play. Because now once we have the volume, we know the molar gas volume, we will essentially be able to find the number of moles. Watseba dipalo tsena di monate jwang. Ha ke nahane le hore lona bana towe le tshwarela. Ha ke lwane le lona. Fela ke a le ruta he. Lona bana bese ne ke batla hore bana bese seng bana towe le ntshwarela. Ha ke le telle ne. Never ke le telle. So hantle ke leka hore bana beso wa bona ntho tsena di monate jwang. Ha ke tsebe hore hobaneng le re di thata. Mohlomong ha le shebe dintho ka tsela, ha ke tsebe. Empa he le tla njwetsa hore ho etsahalang hantle. Ho etsahalang. All right, so now 4.2 we have a bit of an understanding right there. Let me just drink my Coke a little bit so that we can continue. But now, how do I pause this thing? Yeah, when? The things that happened here, I could say, something wrong happened here. Now, how do I pause this thing? Kwenzeke izinto ezibhaya la. Jonga ke ngoku into eyenzeka. Yeah, toch. There you are. All right, I have had my nice Coke. It tastes like you. Empa he, but tata bateng ha ke batle lo bua ka bona. So now that we know we are dealing with this story here, we're collecting this carbon dioxide at STP, meaning we can be able to find the number of moles. That was the message being given to us here. Now it says state Avogadro's law. Wow, again, textbook work, guys. Please don't write any exam without having revised the definitions. And please don't cram the damn things. Understand them so that whenever you get stuck, you have things to remind you what can be done there. Okay, let's go, guys, before I waste time. Hey. 4.2.1. So Avogadro's law states something like this. It says at constant temperature, at constant temperature and pressure, which is exactly what we are talking about, the STP. Ne? What is the story? The volume of a gas. Okay, it can be any gas, but let's not be silly. Let's say the volume of a gas, because if we start saying any gas, we might get ourselves into trouble, is directly proportional, okay, to the number of moles, to the number of moles, okay, of gas present, okay, in that particular container. All right, okay, all right. So technically, this is how we got our general gas equation. So if you forget this thing, think of this one, PV equals nRT. Now, if you divide by this bloody business right there, I'm sorry for the language, guys, you will end up with V equals nRT over P. Now, we can see that these two at STP are constant. This is the general gas constant. Then we can see that the V is directly proportional to N. Okay? So please guys, these things are easy, man. You just need to learn your craft properly. So essentially, the general gas equation is your guide to Avogadro's law, because that way you start smiling and never stopping. Otherwise, that is the 2 marks that we are talking about. Easy stuff. So let's see, 4.2.2. It says now calculate the number of moles of carbon dioxide produced. See, 3 marks, pretty easy. So we know that the number of moles of CO2 is going to be the volume we obtained divided by the molar gas volume at STP, because that's the story. So we got what? 0.336 divided by, now we know that this is 22.4 decimeter cubed. And it will give us the number of moles. So 0.336 divided by 22.4. This is now 0.015 moles. All right, not a problem. So we are doing great. So that was easy. Formula, substitution, answer. Do you see this question? We saw it in the MCQs. We used it and we're using it again. So there's no way you are failing this exam unless you are really problematic, a person on earth. And me, I will kill you. Please come to me. I'm more than willing to kill somebody. I will hang you by the shoelaces so that by the time you're trying to check out and you've already bowed and peed on yourself, that thing will snap and you'll be crying here, and I'll be slapping you around a bit. Alright, masiqhubekeni ke ndingekaniphathisi ubuso nje msinya ukudibene nokungxama nokukhawuleza yona yonke loo nto. Into eputlakile ngihambe. Calculate the number of carbon dioxide molecules in the sample collected. That is the number of molecules. Basically the number of molecules is going to be the number of moles multiplied by the Avogadro number. That is the story like that. So this question is easy, Buffett. 0.015 into, what is that one? I forgot. Avogadro stuff. There is a Planck's constant. Yewena ningazongenza njalo phela. Konje Avogadro 18 nakanini. Saba sengxakini ke ngoku. Ibifanele uba lapha kwi-constants nje. Hayi wena. Nesiqhela ke manje. Senisijwayele kakhulu. Kutheni ngekho Avogadro's constant? Hayi ke bafowethu. Angisazi heke emanje. Kanimeni kancinci ndiyifuni. Okay guys, I got it. Ngisokolileke manje. Funana nama past question papers. Anyway, that should be in the formula sheet. I'm surprised it was not included in the constants. So we've got 0.015 into 6,02 times 10 to the 23. So we're getting here 9,03 times 10 to the 21 molecules. This is not the same as moles, eh? Maybe it is, yeah, whatever, man. So that is the number of molecules or atoms, if you were to ask me. How many atoms are in there? That's the same story. Molecules or atoms of carbon dioxide. That is easy, ne? Pretty straightforward. Nothing serious there. So you've got an equation, substitution, answer. They were just gifting you marks even. It's a very lousy question after all. Now let's see. Yeah, it's 2 marks. Yeah, it's really ridiculous if you ask me. It's ridiculous. But yeah. Anyway, do we really have to care about the marks they're giving? We don't. Now let's move on. 4.2.4 says, calculate the mass sodium chloride formed in this reaction. Okay, so we're going to use what we know. What we know is the number of moles of carbon dioxide we produced. And this is a 2:1 or 1:2 situation. So we can just simply say the number of moles of NaCl is going to be equal to 2 times the number of moles of CO2 produced. Okay? Nice and easy. So this is 2 into 0,015. So we're using molar ratios here. Nice and easy. So 2 into 0,015. We're getting a 0,03 moles. Okay? Now, once we've got this one, I don't know why my mole is trying to be nasty there. Now what do we want? We want the mass. So we can say therefore, or maybe let's not start there. We know that, okay, but the number of moles of NaCl is equal to the mass divided by its molar mass. So we can say this therefore tells us that the mass of that one that we produced is going to be the number of moles multiplied by the molar mass. This is 0,03 into the molar mass. Sodium is what? 23 plus chlorine, that is 35,5. Is that SWA? Let's double check. Sometimes the brain gives up the ghost. Sodium, yes, is 23. Yeah, when I must get a Kogele business. So this is 0,03 into 23 plus 35,5. So we've got here 1,76 grams of sodium chloride that we produced. So it's quite a lot, is it not? Yeah, you can cook food. You can cook food with this one. You can cook food and eat and be fine. So usually once you see a 4-mark question, you are going to do 2 steps, usually. So essentially, this story is very important and that number of moles is pretty intense. And then we know that the formula and the answer will give us the other marks. Sometimes too much substitution is not really impressive. At the same time, we can easily ignore that one. But because this molar mass was a calculation, we can focus on it. It doesn't matter. Once you've got it all correct, the marks are just your friend. Now it says define the term concentration in words. Is the ability to concentrate in class, is it not? Okay, not necessarily. Concentration basically is the amount of substance dissolved in a unit volume. So it is the amount of substance dissolved in a unit of volume. Sometimes they use a liter, so you can say per liter. So it's the amount of substance in moles per unit volume. Easy stuff. So there's plenty of ways to, but I mean easy definitions, guys. There's no need for a second invitation there. Now, if the concentration of the hydrochloric acid is 0.1 mole per decimeter cubed, what is the minimum volume of hydrochloric acid needed for the reaction to run to completion? Okay, all right, okay. This one is another nasty one, too. Oops, 2.2. Kutheni sino-2 ngoku? Avelaphi? Andihlanyela. Batauwe jwale. Abaningi ha ke a mema bo 2 point some change. Nekina libo 4 something. Now let's see something there. So we're given the concentration. Basically, all we want Bafwet is the number of moles, because the number of moles will tell us the volume that we need. So essentially, if we can say all the hydrochloric acid is used up, meaning it is the rate limiting reagent, that is the story that we're being told here. If we take our hydrochloric acid as our rate limiting reagent, I like these things. This is the rate limiting reagent, RLR. That's what we are trying to suggest here, because we don't know anything about the sodium carbonate. And we don't want to know also because they didn't talk about it. We're not going to go into it. So technically, we're going to use what we have, the number of moles of carbon dioxide, because that helps us a lot. We're pretty confident about it. We know that 1 mole of carbon dioxide was produced from 2 moles of hydrochloric acid. Then we can use those molar ratios to get the number of moles of HCl, in which case this will help us to essentially go into finding that volume. Now let's go for it. So technically, we know that the number of moles of HCl is going to be 2 times the number of moles of carbon dioxide produced. Is it not? Because it's 2:1. This is 2 into 0.015, right? That was the story. So, and it's going to be the same as the thing we just did above, you know. Yeah, so this is going to be 0.03 mole. Maybe we should have used the sodium chloride because it's a 2:2 ratio. So essentially the same number of moles. We can now say, okay, all right, we know for a fact that technical concentration of HCl is going to be equal to the number of moles divided by the volume. Now if we want the volume, this implies this therefore concludes that the volume of HCl that we need is going to be essentially number of moles over the concentration, which number of moles is 0.03 divided by, now what is that concentration that they gave us is 0.10, which I don't like to write like that, but let's just do it. 0.03 divided by 0.10. So this is now 0.3 decimeter cubed. So that's the volume that we need. That's the volume that we need. If we make this dude our rate limiting reagent. Crazy stuff, is it not? So again, when you see 4 marks, you should already keep in mind that if you don't have a single formula that is a bit complicated, you are not going to escape the situation of having at least 2 situations considered. So what matters is finding the number of moles of HCl that have reacted in this scenario. Because once you talk of completion, it means that hydrochloric acid must be gone. Okay? And when it finishes, then there's nothing left. Is it not so? It is so. And then we've got a mark for the formula, mark for the substitution, and an answer. So that's how we get our 4 marks. Or, because this is pretty easy and it's all now given, we may not get a mark for the substitution here. Perhaps the mark is in there. I don't know. You decide where those marks are. Okay, let's get to the last question, guys. We are doing fine. 4.3 says 50 grams of magnesium carbonate. Again, we're dealing with a metal carbonate. Oops. Okay. Is added to 50 centimeter cubed of hydrochloric acid. Oops. It's an acid-base reaction again, with a concentration of 0.75 mole per decimeter cubed. Now the equation for the reaction, again, you guys are being spoiled. I keep saying it. You need your brains to be stretched. You need to know how to form these chemical equations and balance them, please. Otherwise, what's the point? Your brains are now being trained not to think, which is bad. So we must stretch those brains so that they can work. Okay? You will thank me later. Please make an attempt of doing this before they even... So when you see this, when you're practicing, of course, don't do it in the exam. When you're practicing, just close that part and figure out that formula, that chemical equation, and balance it. Then compare with what they're giving you. Because we don't want lazy minds showing up as the best in the country. You're getting 100%, but you don't know how to form chemical equations and balance them. That's dangerous, is it not? Because it will give us the impression that you know this subject, but technically not really getting it right. Nah. But of course, I'm not against you guys succeeding. I mean, they have to simplify your lives to some extent because, yeah, it can be torturous sometimes. But I believe that through struggles, a lot of character change happens, and essentially it changes for the better most of the time, because it instills in you a bit of patience. It instills in you a fear of ever being delayed again. Therefore, you become vigilant, you concentrate, and you make sure that things are in order. It could take a slight mistake that you can easily rectify for you to keep things going forward. But if things are made easy, you make so many big and costly errors that are nasty, but you won't notice them until everything is broken down. And that means you will be stalled going forward, even in the future. You don't want such a bleak future when you actually had a bright start. It is even better to have a bleak start for a brighter future, is it not? Because that is a showcase. Anyhow, let's do our business just the way we know it. And then we are told the carbon dioxide gas is collected at STP. Of course, in metric, they don't even mention this. They leave you to just assume it at times. So I'm glad that they actually have this in mind, because sometimes it's illegal to use that formula when you do not have the statement given forward. It's dangerous. Ne? So that statement is actually noteworthy. It's noteworthy. Okay, bafethu ngizama ukukhokha umoya ngikhathele kahle kahle. Anyway, 4.3.1, what are the standard conditions used when conducting an experiment at STP? Easy stuff, bafowethu. So this is 4.3.1. We know that the temperature should be 25 degrees Celsius or 398 kelvins. Is it 3 or 2? It's 298. We will just add 273 there, so it becomes 298 kelvins. We know that when you're talking about pressure, it's 1 atmospheric pressure. I forgot how I forgot how to write the pascals or the kilo. I think it's 100 kilopascals, and then it's some silly number. Let's just check. Do we have these things here? Sometimes they give them, sometimes they don't. So it can be pretty embarrassing at times. You know. They sometimes embarrass us. So they wrote this one's in Afrikaans. A standard. What? Standard rag. Or standard rag. Ja, ek probeer leer Afrikaans now. That is 1,013. So that is the stuff there. That is 1,013 times 10 to the 5 pascals. Or you can equate that thing to 100 kilopascals. So that's the one. And then, of course, standard temperature and pressure, and even the standard volume, or we can say the molar gas volume, should be that 22, whatever. So the volume there should be 22,5, but I mean, it doesn't matter, this one. The standard STP is basically standard temperature and pressure. How many marks are they giving here? If they're giving 3 marks, we're going to throw in the volume. Yeah, the volume is really not. It's a means to an end, essentially. So those are the 2 ones. Thank you. Realebo. Onale botho man. Wa re fa fela hore re nke re tsamaye. A ke rate he po yeno ya hore re tsa. Ske la re retsa bana bese. Ke le kopa hle. Ha ke le boeng hantle man. Wa bona? Le bontsha hore hore leba nako tsena tsa bo 2000 some change, isn't it? Thina ngela xesha yes bingamabhongo hore akere, but now be a bit sophisticated man. Ere kere bare wayibona ntwini emanate nice. Determine which reactant is the limiting reagent. Wow. Yeah, now they are starting to punish a student who is bunking class. Now, technically, if you don't bunk class, this is not going to embarrass you. But if you bunk classes, you're going to be dead. And please come to me. Now, how do we start? Basically, we need to start with the stuff that we know. Okay? Because the stuff that we know will tell us the stuff that we need to know. Now, what are the 2 reactants here? It's hydrochloric acid as well as the magnesium carbonate. Now, of the 2, which one is the rate limiting reagent? So which one do we have information about? We have got information about hydrochloric acid. So let us work on that. Just right. Okay, all right, okay. I'm trying to figure out, should we ignore the carbon dioxide? I'm not too sure, but we will see. Let's start with the number of moles, because what we need is the number of moles. So to start this one, we're going to calculate the number of moles of HCl. What are they? So it's going to be basically CV, concentration, which is 0.75, into the volume is going to be 500 over 1000. Okay? Because we need to convert it to decimeter cubed. 0.75 into 500 divided by 1000. So we're getting a 0.375 mole. All right. Okay. All right. Now we've got a bit of a situation here. But anyway, we know we will know the number of moles of magnesium carbonate. Actually, I forgot that we are given the mass. See, sometimes not highlighting information can blind you. So you may think that it's an overkill to highlight things. It's not. It helps you to think, because if you forgot like I just did, you're going to run around and doing wrong things. Now let's see, what is the number of moles of magnesium carbonate? Is going to be the mass over molar mass. The mass is 50 grams. Divide by magnesium is 24 plus 12 plus now CO3, that's 48. 16 by 3, is it 48? 16 times 3, yeah, is 48. Okay, all right, okay. Sekuyahlangana, masibone ukuthi zingakanani la in number of moles. So this is 50 divided by 24 plus 12 plus 48. Oops. So what are we getting here? We're getting 0.595 mole. All right, as you can see, that one is bigger than the one for the HCl. And we can obviously see that we need 2 moles of HCl to react with 1 mole of magnesium carbonate. So essentially, the one that is in excess here, is this one, because this one has a bigger number of moles. Right, all right. So I don't know, what is the story here? So we can just say, since 1 mole of MgCO3 reacts with 2 moles of HCl. And anyway, let's have a look here. Think about it. I mean, that number of moles is already smaller than that. Maybe we can even say N for HCl is smaller. I don't know, guys. Sometimes some questions, they give me a headache because I have not worked with this for a while, so at times my thought process just goes around in circles. Sometimes I also feel ridiculous, It's smaller. It is therefore HCl is a limiting reagent. I don't know. Basically here you compare the number of moles by what. So that is important. This is important. That is important. And that is important. 4 marks. Probably this molar mass is important, 5, and then deciding which one is important. Of course, you know how to go about that business, guys. I don't want to say too much. Let's do the last question. These are the big ones. Sometimes you will meet them in grade 12. They can surprise you with those questions, already with other information added on top. Now they're saying if the percentage yield of the experiment is 85%, calculate the volume of carbon dioxide collected at the end of the experiment at STP. So another big question. So now they're really killing us, are they not? Okay, so 4.3.3. Let's do it. We are right at the end. Now the percentage yield, basically, it's talking about the product, okay? And one of the products is carbon dioxide. So we are essentially going to deal with that story. That is the story of carbon dioxide that we got. Now, when we do percentage yield, it's going to be theoretical versus actual, is it not? Yeah, boy. So it's going to be theoretical versus actual, and then is it actual versus theoretical? Sometimes my brain. Let's see. Is it theoretical? Yeah, the theoretical usually is an overestimation usually. So it's going to be the actual versus theoretical. Ne? Yeah. And then we're going to deal with that just right. But we have a bit of a problem now. We need to be very crafty indeed. We need to be very crafty indeed. All I'm trying to think now, because we need the volume, so we will need the number of moles of what we got. Right. Yeah, this question is giving me goosebumps. Why am I sweating now over such a stupid question? Let's think for a second. We are saying we have 85% of this thing, right? So basically, the percentage yield is going to be the actual over theoretical multiplied by 100%. Now, what do we want? This can be expressed in terms of number of moles. But now we did not hear anything about the number of moles. Because the theoretical is going to be the number of moles. Of course, this one will be expunged completely. Then it will be the one that we can use to get this guy, the carbon dioxide. And then once we get the number of moles of carbon dioxide, we use our stories. But now my problem is that how is this helping? How is this helping? This technically is trying to suggest that we need to find the actual number of moles. Right. So let's see. We're going to start it this way. First, let's get the number of moles, the theoretical one. So we can just say number of moles of CO2 theoretically is going to be equal to half the number of moles of HCl used. Right. Because you always want the limiting reagent, because that's the one that gives you an idea. Because when it goes out of the picture, then everything has stopped. Ne? So this is going to be half of, now we calculated, did we? We did not. Yeah, we did above. So the number of moles were 0.375. So that is the theoretical yield, right? So we're going to take half of that story. So 0.5 into 0.7, no, 375. So we'll be told it's time up, guys, so you need to finish. Of course, you would not be singing like I am doing. So you will definitely do keep time. 0.18. Let's make it 38 moles. Okay. Now that is what we know theoretically. Okay. So now we want to know the volume. Actually, we can forget about it. This one can be the actual volume over the theoretical volume, is it not? Yeah, man. That's where this thing comes in. We can say this implies that the volume of carbon dioxide obtained is going to be the number of moles, which is 0.188, into the molar gas volume, which is 22.5. And of course, this is still theoretical volume, right? This is theoretical. 22.4, man, not 5. Unzango. Hayibo. Awusasebenzi. I span into esilungu. Oh, unborn, so says New Zealand. So this is theoretical, because we're using theory now, right? Right. So let's see. This is 0,188 into 22,4. So this gives us a 4,2112 decimeter cubed. Okay. All right. Okay. Now we know this is the volume that we obtained at STP theoretically, because that is what we're trying to get to. So now we can say, we know that now the percentage yield is going to be actually the actual volume over the theoretical volume multiplied by 100%. Now this implies, now they told us that this is 85%, right? 85% is basically 85 over 100. So this is 85 over 100. Ne? Kutheni ngathi ndifuna uba nengxaki ngoku. Ngibatla huba le mathata. Yeah, man, let's forget about the multiplication by 100. Damn. Okay, now I'm becoming a bit sloppy, folks. So this is just 85% equals. The actual yield is what we want to know. The actual, because that's what they want us to find, over the theoretical volume. We got 4,2112 multiplied by 100%. So technically we divide both sides by 100, so we're going to have 85 over 100. The percentage is dropped. This is now going to be actual volume. They'll be like, hey guys, you're wasting time. You are supposed to get out of the exam room now. This is 4,2112. Here you just cross multiply that. It's a very good gymnastic. So therefore the actual, maybe maybe. So now the actual volume of CO2 is going to be basically 85 over 100 multiplied by 4,2112. So this is 85 over 100. 85 over 100 into 4,2112. So this is basically 3,58 decimeter cubed. So can you see this one is definitely smaller than what in theory we thought we got. In theory we got 4 decimeter cubed, and essentially we got 3 some change, but of course rounded off is almost there. So 85% is quite a good one. So essentially that is the story, guys. So this one was a bit of a big one. So you do not take these ones lightly. So for me, for you, question 4.3, it's N and B. It's a nota bene. Please practice questions along these lines, where you're going to decide which one is the rate limiting reagent, and where you're going to calculate some percentage yield whatsoever. So these are the questions that are going to still haunt you in grade 12. So make sure you understand this stuff. So here we got ourselves into a lot of trouble, I suppose, but not too much. So basically all we needed was the number of moles in theory. Okay, and essentially we needed the theoretical volume as a result, using our molar gas volume constant. So the other thing that we needed, so essentially, was to show this stuff here, and then the substitution there. So we've got 1, 2, 3, 4. And essentially, the answer, the gymnastics are stuff that you need to know. Okay, guys, so that marks the end of our question paper. And I hope you've enjoyed the video and you will have learned something. It's a pity. It's a common paper, so topics were kind of squeezed, so we never got a chance to review some of the term 1 material, and so that you can expand your knowledge a bit better. But we will find other papers which hopefully will have their desired effect of giving you just enough to gain your confidence as you progress with this acquisition of knowledge for future purposes, because in metric this needs to be second nature already. Okay guys, goodbye, see you next time.